this is an iHeart podcast. Guaranteed human.
With no fees or minimums on checking accounts, it's no wonder that Capital One Bank Guy is so passionate about banking with Capital One. If he were here, he wouldn't just tell you about no fees or minimums. He'd also tell you about how Capital One cafes are open 7 days a week to assist with your banking needs. Yep, even on weekends. It's pretty much all he talks about, in a good way. What's in your wallet? Terms apply. See CapitalOne.com/bankguy. Capital One N.A., member FDIC.
Hey everybody, the official Big Bang Theory podcast is back, covering seasons 3 and 4 of the show. Each week, host Jessica Radloff speaks with crew and cast members like Kunal Nair, Mayim Bialik, and Kevin Sussman. Hear about the Easter eggs you may have missed, behind-the-scenes stories, and how certain real-life relationships shaped some of the most memorable storylines. Watch the official Big Bang Theory podcast on HBO Max or wherever you get your podcasts.
Hey everybody, it's me, Josh, your old pal, and for this week's SYSK Selects, I've chosen How Chaos Theory Changed the Universe. It first came out in July of 2016, and I have to say, I think it's one of the better science-y stuff you should know episodes of all time. There's just something about this that grabbed me and Chuck by the collars and said, I'm interesting, aren't I? And we said, yes, you definitely are. And this one has everything. It has science, it has philosophy, it has our understanding of the universe. Is just an all-around good episode. So I hope you enjoy it as much as I did listening to it again.
Welcome to Stuff You Should Know, a production of iHeartRadio's How Stuff Works.
Hey, and welcome to the podcast. I'm Josh Clark with Charles W. Chuck Bryant, and there's Jerry over there. So this is Stuff You Should Know, the podcast about chaos theory. Like, have you ever seen Event Horizon?
I did. Not bad.
Great movie. Are you crazy?
I don't think it was great.
Oh, it's so imaginative.
I thought it was okay.
It was like a Lovecraftian thing in outer space.
Yeah.
Loved it.
It was all right.
I Lovecrafted it.
Yeah.
I liked it. That's what I think of when I think of chaos. You know, there's that one part where they kind of give you like a glimpse behind like the dimension that this action is taking place in.
Yeah.
To see the chaos underneath. And
I should check that out again.
Yeah. I think you should.
I think about Jurassic Park and Jeff Goldblum as the creep. Dr. Malcolm explaining chaos in the little auto driving SUV or whatever that was.
Right.
Yeah.
That's what it was called in the script, the auto driving SUV scene.
Yeah. And you know what? I actually rewatched that scene and it confirmed two things. One is that he actually did a pretty decent job for a Hollywood movie of a very rudimentary explanation of chaos. Yeah. And
you watched it for this?
Yeah.
Oh, okay.
Yeah, just that scene.
Yeah.
And then it also confirmed of what a creep that character was.
Yeah.
If you watch that scene, he's like, he was all gross and flirty with her right in front of her ex.
Right.
But there's this, he's talking to her. I didn't even notice this at first. He just touches her hair out of nowhere for no reason.
Oh, really?
He's just talking to her and he just grabs her hair and touches it. Huh. And I'm like, what a creep.
I know. If you look closely, you can see the hormones emerging through his chest hair.
Yeah.
It's grody.
And I love Jeff Goldblum. It's not a reflection on him.
He was basically doing Jeff Goldblum.
Well, that's what yeah, sure.
He's Jeff Goldblum.
But I don't think that's how, in the manner in which he speaks, but I don't think he's a creep. Do you? Wow.
I've got nothing against Jeff Goldblum.
Oh, okay.
I think he's doing Jeff Goldblum.
It was also a sign of the times. Like if that movie were made today, Dr. What was her name in the movie?
Ellie Sattler, I think?
Yeah, Dr. Sattler would be like, it's very inappropriate to stroke my hair, dude.
Yeah.
Like, don't touch me.
Right.
But this was the 90s. Or was it the 90s?
It was freewheeling.
Or was it No, it was 90s.
It was the early mid-90s, I think. Yeah. 92, 93, 94. The book came out in 1990. And in the book, Ian Malcolm, who's a chaotician.
Yeah, a creep chaotician.
Right. He goes into even more depth about chaos theory.
Sure.
But that was the first time I ever heard of chaos theory was from Jurassic Park.
Yeah, me too, probably.
And it was really misleading. I think the entire term chaos is very misleading as far as the general public goes. as from what I researched in this for this article.
Well, yeah, I mean, you hear the word chaos as a English speaker, and you think frenetic and crazy.
Out of control.
Yeah, and that's not what it means in terms of science like this.
Right. What it means, I guess we can say up front, is basically the idea that complex systems do not behave in very neat ways that we can easily grasp, understand, or measure.
Right, and not even simple systems don't sometimes. Mm-hmm. It doesn't always have to be complex, but I want to give a shout out in addition to our own article.
Ooh.
To when it comes to stuff like this, the brain breaking stuff for me.
Man, this was a brain breaker.
You know how I always go to like blank for kids, right? Because it always helps.
If there's a dinosaur mascot on the page, it's a sure thing we can understand it.
But the best explanation for all this stuff that I found on the internet was from a website called Abarim, Abarim Publications, which turns out to be a website about biblical patterns. Mm-hmm. And sandwiched in the middle there is a really great, easy to understand series of pages on chaos theory.
Nice.
So I was like, man, I get it now. I mean, in a rudimentary way.
Right. Well, yeah. I think even a lot of people who deal with systems that display chaotic behavior, which I guess is to say basically all systems eventually under the right conditions, don't necessarily understand chaos.
Yeah, and they define a complex system as specifically, it doesn't mean just like, oh, it's complex. I mean, it is.
Right.
But specifically, they define it in a way that helped me understand. It's a system that has so much motion, so many elements that are in motion.
Moving parts.
Yeah, that it takes like a computer to calculate all the possibilities of like what that could look like 5 minutes from now, 10 years from now.
Right.
So before computers came around, before the quantum mechanical revolution, it was a lot more basic. It was like, what comes up must come down. Stuff like that.
Let's talk about that, Chuckers, because when you're talking about chaos theory, it helps to understand how it revolutionized the universe by getting a clear picture of how we understood the universe leading up to the discovery of chaos, right?
Yeah.
So prior to the scientific revolution, everybody was like, oh, well, it's God. The earth is at the center of the universe and God is spinning everything around like a top, right?
Yeah.
It was all a theistic explanation. Then the scientific revolution happens and people start applying things like math and making like mathematical discoveries and figuring out that there's order. They're finding order in patterns and predictability to the universe.
Yeah.
If you can apply mathematics to it.
Yeah, specifically if you can apply mathematics to the starting point.
Right. So if you can figure out how a system works, mathematically speaking, right?
Yeah.
You can go in and plug in whatever coordinates you want to.
Yeah.
And watch it go. You can predict what the outcome's going to be. And what this is that it's based on what at the time was a totally revolutionary idea. By initially, I think Descartes was the first one to kind of say, cause and effect is a pretty big part of our universe, right?
Yeah, it was sort of like where, this is 1600s, where early science met philosophy.
Right.
They kind of complemented one another as far as something we're talking about determinism.
Right. So that was the kind of the seeds of determinism was the scientific revolution. And like you said, where philosophy and science came together in the form of Descartes, right?
Yeah.
And then Newton came along and we did a whole episode on him.
Yeah, January of this year.
That was a good one.
It was really good.
Like, I think you said in that episode that there's possibly no scientist that's changed the world more than Newton has.
Maybe.
He's got legs.
People shouted out others in email, but I'll just say he's near the top.
For sure.
With some other people.
The cream.
Yeah.
So Newton came along, and Newton said...
That was his name, Isaac the Cream Newton.
Right.
I think.
And anytime he dunked, he'd be like, cream!
Yeah.
You just got creamed.
Oh, I thought he was a boxer. He's a basketball player.
He was much more well-known as a boxer, but he definitely could dunk as a b-baller.
Yeah.
So, man, that threw me off a little bit.
That's right. The cream.
Yeah, the cream comes along, and he basically says, watch this, dudes. This cause and effect thing you're talking about, I can express it in quantifiable terms. And he comes up with all of these great laws.
Yeah.
And basically sets the stage, the foundation for science for the next 3 centuries or so.
Yeah, these laws that were so rock solid and powerful that scientists kind of got ahead of themselves a little and said, "We're done." Like
Done.
With Newton's laws, we can predict everything if we have a good enough beginning accurate value to plug into his equations.
Yeah.
And they weren't. I think there was a little hubris and a little just excitement about like, well, we figured it all out.
Right, that you could take Newton's laws, and if you had accurate enough measurements, you could predict what the outcome would be of that system that you plug those measurements into using these formula, right?
And at the time, a lot of this was like planetary, like, well, we know that these planets are here and they're moving and they're orbiting. Yeah. So if we know these things, we can plug it into an equation and we can figure out what it's going to be like in 100 years.
Exactly. And they figured out, and the basis of determinism is what we just said, that if you have accurate measurements, you can take those measurements and use them to predict how a system is going to change over time using differential equations, right?
Yeah.
So this is what Newton comes along and figures out, that you can describe the universe in these mathematical terms using differential equations. And like you said, there was a tremendous amount of hubris, and well, I think you said there was some hubris. I think there was a tremendous amount of hubris where science basically said, we've mastered the universe. We've uncovered the blueprint of the universe, and now we understand everything. It's just a matter now of getting our scientific measurements more and more and more exact.
Yeah.
Because, again, the hallmark of determinism is that if you have exact measurements, you can predict an outcome accurately. Like the pool cue example, or the pool table example, right?
Right. So if you've got a pool table, let's say you're playing some 9-ball.
Right.
So you have that beautiful little diamond set up. You got your cue ball. You put that cue ball and you crack it with the cue. And if you are super accurate with your initial measurements, you should be able to mathematically plot out via angles where the balls will end up.
Right, exactly. Like you can say this is what the table will look like after the break. If you know the force, the angle, all those little variables.
The temperature, if there's wind in the room, like the felt on the table, like everything, the more specific you are, the more accurate your end result will be. Right.
And then one of the other hallmarks of determinism is that if you take those exact same initial conditions and do them again, the pool table will look exactly the same after the break.
Yeah, which is pretty much impossible for like a human to do with their hands.
Sure, but the idea at the time of science was that if you could build a perfect machine that could recreate these conditions, it will happen the same way every time, right?
Yeah, and this led to, they had hubris, but you could understand it when, like literally in 1846, 2 people predicted Neptune would exist.
Yeah, within months of
Not
each
would
other.
exist, but does exist.
Right.
And this is not by looking up in the sky. Like, they did it with math.
Right.
And they were right.
Yeah.
So imagine in 1846, when that happens, they're like, yeah, we've got the math down, so we're pretty much all-knowing.
Well, plus also, for the most part, not just with Neptune, they were finding that this stuff really panned out. It held true for everything from the investigation into electricity to new chemical reactions and understanding those. Yeah. And it laid the scientific revolution laid the basis for the industrial revolution. Yeah. And just the change that came out of the world like that. It definitely, it is understandable how science kind of was like, we got it all figured out.
Well, and like you said, they, even Galileo was smart enough to know there's uncertainty in these measurements. Like the precision is key. So they spent, what does the article say? Much of the 19th and 20th century just trying to build better instrumentation to get more and more smaller and smaller and more precise measurements.
Right. That was like basically the goal of it, right?
Yeah, which was the right direction. That's like exactly what they should have been doing.
Yeah. The problem is like you said, Galileo knew that there was some sort of there were going to be some flaws in measurement, that we just didn't have those great scientific instruments yet, right?
Yeah, it's called the uncertainty principle.
Okay.
It prohibits accuracy.
Right. But the idea is that if you have a good enough instrument, you can overcome that. And that the more you shrink the error in measuring the initial conditions, the more you're going to shrink the error in the outcome.
Yeah.
It'd be proportionate, right?
They were correct.
The thing is, they were also aware, but ignoring in a lot of ways, some outstanding problems, specifically something called the n-body problem.
Yeah, you know what? I'm so excited about this. I need to take a break.
I think that's a good idea.
I need to go check out my n-body in the bathroom.
Okay.
And we'll be back.
The springtime thaw is finally here. Flowers are blooming. Days are longer. We're saying yes to more plans and finally getting outside, running, walking, just moving again. It's the perfect time to upgrade your everyday go-tos with Bombas. Take Bombas sport socks. They're super comfortable and designed with sport-specific tech for running, cycling, yoga, hiking, you name it. I use them to run in, and I can tell you they work beautifully. So head over to bombas.com and use code SYSK for 20% off your first purchase. That's BOMBAS.com, code SYSK at checkout.
Hey, everybody. Here's a fact for you. In the United States, there is a break-in every 26 seconds, and that means that somewhere right now, an intruder is getting closer. And the problem with most security systems is that they only alert you after the break-in has started, and that's too late.
Well, that's what makes SimpliSafe different. They use alerts. SimpliSafe's U.S.-based live agents, they identify threats on your property and help deter them before they actually break in. So the intruder never gets into your house. The crime is stopped before it even starts.
That's right. And another great thing about SimpliSafe is they have no long-term contracts. They give you peace of mind and great value with their monitoring deterrence plans because they just start at about $1 a day.
Yeah, SimpliSafe sent us a setup years back, and I still use mine every day.
Yeah, and apparently setup, you can do it by yourself in under 30 minutes, so it's a really good value and it doesn't take long.
So if you want to experience the SimpliSafe peace of mind, you can take advantage of the SimpliSafe discount offered to Stuff You Should Know listeners. Right now, you can get 50% off your new system by visiting simplisafe.com/stuff. That's half off at simplisafe.com/stuff. There's no safe like SimpliSafe. All right, Chuck, we're back. So there's some issues, right, with determinism. There's some weird problems out there that are saying hey, pay attention to me, because I'm not sure determinism works.
Right.
And one is the n-body problem.
Yeah, how this came about was in 1885 there was King Oscar II of Sweden and Norway.
Yeah.
Don't want to leave out Norway. Both. He said, you know what, let's offer a prize to anyone who can prove the stability of the solar system, something that has been stable for a long time before that. And a lot of the most brilliant minds on planet Earth got together and tried to do this with mathematical proofs, and no one could do it. And then a dude named Henri, you got to help me there with that last name.
Poincaré.
Ooh. Say the whole thing.
Henri Poincaré.
Very nice. He was French, believe it or not. And he was a mathematician, and he said, you know what? I'm not going to look at this big picture of all the planets in the sun and all their orbits.
You'd have to be a fool to try that.
Sure. He said, I'm going to shrink this down, like we talked about, shrinking that initial value.
Right.
You know?
Yeah.
And that initial condition. And he shrunk it down. He said, I'm going to look at just a couple of bodies orbiting one another with a common center of gravity, and I'm going to look at this. And this was called the n-body problem.
Yeah, which was smart to do because the more variables you factor into a nonlinear equation like that, the harder it's going to be. So he shrunk it down. So the n-body problem has to do with 3 or more celestial bodies orbiting one another. So Poincaré said, I'll just start with 3.
Yeah, smart.
And what he found from doing his equations for this King Oscar, the sequel prize, was that shrinking the initial conditions, measurement or rate of error, right?
Yeah.
Did not really shrink the error in the outcome,
Right.
which flies in the face of determinism. What he found was that just very, very minute differences in the initial conditions fed into a system
Yeah.
produced wildly different outcomes
Yeah.
after a fairly short time.
Yeah, like let me just round off the mass of this planet at like the 8th decimal point.
Right.
And like, who cares
Who cares?
at that point?
Yeah.
Let me just round that 1 to a 2.
Right.
And that would throw everything off at a pretty high rate.
Right.
And he said, wait a minute, I think this contest is impossible.
Right. He said there is no way to prove the stability of the solar system because he just uncovered the idea that it's impossible for us to predict the rate of change
Yeah.
among celestial bodies.
Yeah, it's such a complex system. There are far too many variables that it's impossible to start with something so minute to get the equation or whatever, the sum that you want at
Right.
the end.
Well, not only
Well,
that.
not a sum, I guess, but the result.
Not only that, and this is what really undermined determinism, was that he figured out that you would have to have an infinitely precise measurement,
Yeah.
which even if you built a perfect machine that could take a perfect machine that could take a measurement of like the movement of a celestial body around another,
Yeah.
it's literally impossible to get an infinitely precise measurement.
Yeah.
Which means that we could never predict out to a certain degree the movement of these celestial bodies. Like he was saying, like, no, you can't build a machine that gets measurements enough that we can overcome this. Like determinism is wrong. Like you can't just say we have the understanding to predict everything. There's a lot of stuff out there that we're not able to predict, and he uncovered it trying to figure out this n-body problem.
Yeah, and King Oscar the sequel said, "You win.
Yeah.
Bring me another rack of lamb, and here's your prize."
Yeah.
And he won by proving that it was impossible, which is pretty interesting.
And that utterly and completely changed not just math, but like our understanding of the universe and our understanding of the universe, which is even more kind of earth-shaking.
Yeah, he discovered dynamical instability or chaos, and they didn't have supercomputers at the time, so it would be a little while,
right?
About 70 years at MIT until we could actually kind of feed these things into machines capable of plotting these things out in a way that we could see.
Right.
Which was really incredible.
So there was this dude 70 years later named Edward Lorenz.
Yeah, well, first of all, we should set the stage. The reason this guy, he was a meteorologist and scientist.
Right.
Not that those are not the same thing.
Right.
He's a scientist who dabbled in meteorology.
Right. He was a mathematician.
Yeah. But he was really into meteorology because there was a weird juxtaposition at the time where we were sending people into outer space, but we couldn't predict the weather.
Yeah, and it was definitely a blot on the field of meteorology.
Sure.
People were like, "Do you guys know what you're doing?"
Yeah.
And meteorologists were like, "You have no idea how hard this is."
Yeah.
Like, yeah, we can predict it a couple days out, but after that, it's totally unpredictable. It drives us mad. And it wasn't just their reputations that were at stake. Like, people were losing their lives because of it, right?
Yeah, in 1962, there were two notorious storms, one on the East Coast and one on the West. The Ash Wednesday storm on the East and the Big Blow on the West that killed a lot of people, cost hundreds of millions of dollars in damage.
Right.
And people were like, we need to be able to see these things coming a little more.
Right.
Because it's a problem.
And meteorologists were like, why don't you do it then?
So they thought the key was these big supercomputers. Remember the supercomputers when they came out, the big rooms full of hardware.
Yeah.
It was amazing. And they were finally able to do like these incredible calculations that we could never do before.
I know. They were able to like crunch 64 bytes a second.
Yeah, we had the abacus and then the supercomputer.
Right.
There's nothing in between.
I looked up the computer that Lorenz was working with.
Was it the Whopper?
A Royal McBee. What was the Whopper?
War Games.
Was it called the Whopper?
Yeah. WOPR.
Right. I can't believe they called it that.
I know. Pretty stupid.
So the guy just nicknamed it Joshua?
No, Joshua was the
Software?
Falcon was the old man who designed all this stuff, and his son was Joshua, and that was the password to get into the system.
Was the password.
Yeah.
I guess I was too young to understand what a password was.
Yeah.
Okay.
Well, you didn't even. There weren't passwords at the time.
No.
Password
and you
was a
just
game
shouted
show.
it at the computer, and they're like, okay, access granted.
Yeah. Still, that movie holds up.
Does it really?
Oh, totally.
I got to check it out.
Yeah, still very, very fun. Young Ali Sheedy, boy, I had a crush on her from that movie.
She was great.
Yeah.
What else was she in recently? Wasn't she in something?
Well, I mean, she kind of went away for a while and then had her big comeback with that indie movie, High Art.
No,
But that was a while ago.
Has she been in anything else recently?
Sure. I think I saw her in something recently, and I didn't realize that was her.
Oh,
Like,
really?
she looks familiar. I was like, oh, that's Ali Sheedy. I don't know.
All right.
I could look it up, but I won't.
It doesn't matter.
Anyway, I still crush on her.
So the Royal McBee was not quite the Whopper. You could actually sit down at it.
The Royal McBee?
That's the name of
That
it.
sounds like a hamburger, too.
It was by the Royal Typewriter Company.
Huh.
And they got into computers for a second. And this is the kind of computer that Lawrence was working with.
Yes.
And it was a huge deal. Like you were saying, Abacus supercomputer.
Yeah.
But it was still pretty dumb as far as what we have today is concerned. But it was enough that Lawrence and his ilk were like, finally, we can start running models and actually predict the weather.
Yeah.
So he started doing just that.
He did. So he started off with a computational model of 12 meteorological
I liked how you said it.
calculations, which is very basic because they're infinite meteorological calculations, probably.
Yeah.
Depending. Did I say it wrong again?
No,
Okay.
It sounds like you're about to say it wrong, and then you pull it out at the last second.
Maybe.
It's really impressive.
But so that's very basic, but he wanted to start out, with something attainable.
Right.
So he narrowed it down to 12 conditions, basically, 12 calculations that had, temperature, wind speed, pressure, stuff like that.
Right.
Started forecasting weather. And then he said, it'd be great if you could see this. So I'm going to spit it into my Wonder Machine, the McWhopper. What was it?
The Royal McBee.
The Royal McBee. And I'm going to get a printout so you can visualize what this looks like.
Right.
So things were going well, and he had this printout, and everyone was amazed because these calculations never seemed to repeat themselves.
He was making like word art. You remember that? Like that was the first thing anybody did on a computer.
Oh yeah.
Was to make word art, like a butterfly or something.
Right. You would print out. I never could do that.
I couldn't either.
Like you have to be able to visualize things spatially. You have to have that right kind of brain for that.
Right, or you have to be following a guidebook that tells you how to do it.
True.
Have you ever seen Me, You, and Everyone We Know?
Yeah, I love that movie.
That's a great movie.
Yeah.
Those little kids in there, they were doing that.
Oh yeah.
The forever back and forth poop.
Well, I haven't seen that since it came out. It's been a while.
Oh, you got to see it again.
Yeah.
Great movie.
Good movie.
Ali Sheedy's not in it.
No.
It's Miranda July.
Right, and she wrote and directed too, right?
She did a great job.
It was her show.
It's one of those rare movies where, there's just the right amount of whimsy. Because whimsy so easily overpowers everything else and becomes bleh.
Yeah.
This is the most perfectly balanced amount of whimsy I've ever seen in a movie.
Yeah, if there's too much whimsy, I just
terrible.
Garden State. I just want to punch it in the face.
Terrible. Although I like Garden State, but I haven't seen it since it came out.
It hasn't aged well.
Yeah.
It's just, when you look at it now, it's just so cutesy and whimsical.
Oh, yeah.
It's come on.
Yeah.
Boy, we're getting to a lot of movies today.
Oh, yeah, well, we're stalling.
We haven't even talked about Butterfly Effect yet, which is coming.
It is. I'm dreading it. That's why I'm stalling.
All right, so where were we? He was running his calculations, printing out his values so people could see it. And then he got a little lazy one day in 1961. This output, he noticed, was interesting.
Right.
So he said, I'm going to repeat this calculation, see it again. But to save time, I'm just going to kind of pick up in the middle. And I'm not going to input as many numbers but I'm still using the same values, just I'm not going out to 6 decimal points.
So the printout he had went to 3 decimal points.
Yeah.
So he was working from the printout and didn't take into account that the computer accepted 6 decimal points. So he was just putting in 3.
Correct.
And expecting that the outcome would be the same, right?
Yes, but the outcome was way different.
Right.
And he went, whoa.
What?
Yeah. He's like, what's going on here? It was a big deal. I mean, someone would have come up with this eventually, probably.
Yeah,
but he sort of accidentally came upon it.
It's neat that this guy did this because it changed his career. I think he went from emphasis on meteorology to an emphasis on chaos math.
To stud scientist.
Basically. So, I mean, the guy's got an attractor named after him, you know what I mean?
Yeah, well, let's get to that.
So Lorenz starts looking at this and he's like, wait a minute, this is weird. This is worth investigating. And like what was his name? Poincaré?
Yeah.
He said, I need fewer variables. So I'm not going to try to predict weather with these 12 differential equations that you have to take into account. I'm just going to take one aspect of weather called a rolling convection current. And I'm going to see how I can write it down in formula form. So a rolling convection current, Chuck, is where, you know how the wind is created, where air at the surface is heated and starts to rise. Yeah. And suddenly cool air from higher above comes in to fill that vacuum that's left. And that creates a rolling or vertically based convection current.
Yeah.
Okay?
I would describe it as oven.
Oven, boiling water, cup of coffee.
Sure.
Wherever there's a temperature differential based on a vertical alignment, you're going to have a rolling convection current, okay?
Yeah, it sounds complex, but he just picked out one thing, basically, one condition.
Right.
And this is the one he picked out.
But had you seen my hands moving, listeners, you would be like, oh, yeah, I know what you're talking about.
He made little rolly motions.
So he's like, okay, I can figure this out. So he comes up with three formulae that kind of describe a rolling convection current. And he starts trying to figure out how to describe this rolling convection current, right?
Correct.
And so, like I said, he got these 3 formulae, which were basically 3 variables that he calculated over time. And he plugged them in, and he found 3 variables that changed over time. Mm-hmm. And he found that after a certain point, when you graph these things out, and since they're 3, you graph them out on a 3-dimensional graph, so X, Y, and Z.
Again, he wanted to just be able to visualize this.
Right.
Because it's easier for people to understand.
He was a very visual guy.
Totally.
All of a sudden, it made this crazy graph that where the line, as it progressed forward through time, went all over the place. It went from this axis to another axis to the other axis, and it would spend some time over here, and then it would suddenly loop over to the other one, and it followed no rhyme or reason. It never retraced its path, and it was describing how a convection current changes over time, right?
Yeah.
And Lorenz is looking at this. He was expecting these 3 things to equalize and eventually form a line.
Yeah.
Because that's what determinism says. Things are going to fall into a certain amount of equilibrium and just even out over time. That is not what he found.
No.
And what he discovered was what Poincaré discovered, which was that some systems, even relatively simple systems, exhibit very complex, unpredictable behavior, which you could call chaos.
Yeah, and when you say things were going all over, like if you look at the graph, it's not just lines going in straight lines bouncing all over the place randomly.
Right.
Like there was an order to it, but the lines were not on top of one another. Like let's say you draw a figure 8 with your pencil, and then you continue drawing that figure 8, it's going to slip outside those curves every time unless you're a robot.
Sure.
And that's what it ended up looking like.
Yeah. It never retraced the same path twice, ever. It had a lot of really surprising properties. And at the time, it just fell completely outside the understanding of science, right?
Yeah.
Luckily, this happened to Lorenz, who was curious enough to be like, what is going on here? And again, he sat down and started to do the math and thinking about this, and especially how it applied to the weather, right?
Yeah.
And he came up with something very famous.
Yes, the butterfly effect.
Yes.
This thing kind of looked like butterfly wings a little bit.
Yeah.
And B, when he went to present his findings, he basically had the notion, he's like, I'm gonna wow these people in the crowd in 1972. It's a conference that I'm going to, and I'm gonna say something like, the seagull flaps its wings and it starts a small turbulence that can affect weather on the other side of the world.
Right.
The small little thing will just grow and snowball and affect things. And he had a colleague who was like, seagull wings, that's nice.
Right.
And he said, how about this? And this is the title they ended up with. Predictability, does the flap of a butterfly's wings in Brazil set off a tornado in Texas? And everyone was like, whoa. Minds blown.
Yeah.
Should we take a break?
Yes.
All right, we'll be right back. Hey, everybody. Here's a fact for you. In the United States, there is a break-in every 26 seconds, and that means that somewhere right now, an intruder is getting closer. And the problem with most security systems is that they only alert you after the break-in has started, and that's too late.
Well, that's what makes SimpliSafe different. They use alerts. SimpliSafe's U.S.-based live agents, they identify threats on your property and help deter them before they actually break in. So the intruder never gets into your house. The crime is stopped before it even starts.
That's right. And another great thing about SimpliSafe is they have no long-term contracts. They give you peace of mind and great value with their monitoring deterrence plans because they just start at about $1 a day.
Yeah, SimpliSafe sent us a setup years back, and I still use mine every day.
Yeah, and apparently setup, you can do it by yourself in under 30 minutes, so it's a really good value and it doesn't take long.
So if you want to experience the SimpliSafe peace of mind, you can take advantage of the SimpliSafe discount offered to Stuff You Should Know listeners. Right now, you can get 50% off your new system by visiting simplisafe.com/stuff. That's half off at simplisafe.com/stuff. There's no safe like SimpliSafe.
Work can be a little weird. One minute you're in a meeting that could have been an email. The next you're trying to decode corporate jargon that somehow means nothing. And don't even get us started on the quick sync that turns into a 45-minute deep dive.
Yeah, well, the truth is figuring out your career isn't always straightforward. Whether you're trying to grow, pivot, or just stay relevant, it can feel like you're navigating it all on your own. Well, that's where LinkedIn comes in.
That's right. LinkedIn can help you grow your career, helping you confidently navigate your path with insights, ideas, and inspiration from your professional community. You can stay up to date with the latest trends in your field, connect with people who get it, and discover opportunities tailored to your goals, your experience, and what actually matters to you.
Whether you're looking for something new or just trying to grow where you are, LinkedIn gives you the tools and connections to move forward with confidence. Because LinkedIn is the network that works for you. Visit linkedin.com/knowstuff to learn more. Hey everybody, we're here to talk to you about Wayfair, who believes that spaces should be functional, they should be comfortable, they should be well-designed, and they can be well-designed by you with their help.
Your updated space should feel more comfortable, inviting, and practical for everyday use. And we're talking about outdoor seating. We're talking about grills. We're talking about major appliances. If you need storage solutions, Wayfair can help you out. Patio lighting, rugs, decor. It is your one-stop shop for home.
Yeah. I mean, it's getting nice out, so it's time to think about living outdoors for the next few months. And Wayfair knows that outdoor furniture, it's heavy, it's intimidating to assemble. So Wayfair has stepped in and said, we're going to handle the hard part so you don't have to.
That's right. You can shop Wayfair Verified, your shortcut to the good stuff. And that means their team of product specialists are going to vet everything by hand using a 10-point inspection, testing things like, quality materials, functionality, and features, and even how long it takes to build that piece of furniture. And the overall experience save time, reduce hassle, and improved convenience.
Patio season is here, and these deals won't last. So head to wayfair.com right now to get your outdoor space ready for way less. That's WAYFAIR.com.
Wayfair, every style, every home.
Hey everybody, I want to talk to you a little bit about Tide Evo because it represents over 10 years of innovation and product development. Tide Evo is a first-of-its-kind technology where tens of thousands of minuscule fibers are spun together to form a 6 times powerful layer packed with scrubbers, brighteners, pre-treaters, and fresheners. And that's going to deliver a breakthrough clean that's so powerful, it feels like magic.
Yeah, it is kind of like magic. Tide Evo is revolutionary. A 100% concentrated, waterless laundry tile that's made of compressed microfiber soap layers rather than liquid or powder. And it's not like pods or sheets because it uses 6 layers of detergent fibers to deliver superior cold water cleaning without plastic packaging of any kind. And it provides a mess-free, lightweight solution that dissolves lickety-split. So whenever you run into a laundry challenge, turn to Tide Evo. It's revolutionary. It's magic. Try new Tide Evo. Real laundry magic.
All right, so the Lorenz attractor is that picture that he ended up with.
Right, that graph.
The Lorenz attractor. And this biblical pattern website that I found described attractors and strange attractors in a way that even dumb old me could understand.
What you got?
So if I may, he says, all right, here's the cycle of chaos. He said, actually, I don't know who wrote this. Could have been a woman, could have been a small child.
Could have been Noah.
Of undetermined gender. I have no idea.
So the gender-neutral narrator.
He said, all right, think about a town that has like 10,000 people living in it. To make that town work, you got to have like a gas station, a grocery store, a library, whatever you need to sustain that town.
Okay.
So all these things are built. Everyone's happy. You have equilibrium. He said, so that's great. Then let's say you build someone comes and builds a factory on the outskirts of that town, and there's going to be 10,000 more people living there.
Right, and they don't go to church.
Maybe so. Did I say church? They needed a church?
No.
Oh, okay.
I was just assuming this is what's going to break
website?
The equilibrium.
No. Yeah. But you just have more people, so there's you need another gas station and another grocery store, let's say.
Uh-huh.
So they build all these things, and then you reach equilibrium again. It's maintained because you build all these other systems up.
I see.
That equilibrium is called an attractor.
Okay.
So then he said, they said.
He, capital He.
The royal he said, all right, now let's say instead of that factory being built, you have those original 10,000, let's say 3,000 of those people just up and leave one day.
Okay.
And the grocery store guy says, well, there's only 7,000 people here. We need 8,000 people living here to make a profit. So I'm shutting down this grocery store. Mm-hmm. Then all of a sudden you have demand for groceries. So things go on for a little while, and someone comes in and say, hey, this town needs a grocery store. They build a grocery store.
Right.
They can't sustain. They shut down. Someone else comes along because of the demand. And it is this search for equilibrium, this you reach equilibrium here and there as the store opens.
Periods of stability.
And that dynamic equilibrium is called a strange attractor. So an attractor is the state which a system settles on. Strange attractor is the trajectory on which it never settles down but tries to reach the equilibrium with periods of stability.
Man.
Does that make sense?
That Bible-based explanation was dynamite. I understand it better than I did before. And I understood it okay before. That's great.
Surely you can add. Yeah?
Yeah.
No, you're going to add to it?
No.
That's it?
No, I mean, like an attractor is where if you graph something and eventually it reaches equilibrium, it's a regular attractor. If it never reaches equilibrium, it is constantly trying to and has periods of stability, strange attractor. I can't top that.
All right. Grocery store, small town.
That was great. So Lorenz's strange attractor was named a Lorenz attractor, named after him. Big deal.
They weren't using the word chaos yet.
No, but he published that paper about butterfly wings, right?
Yeah.
The butterfly effect. And it, coupled with his picture, the picture of a strange attractor, which is almost aside from fractals, almost the emblem or the logo for chaos theory, the Lorenz attractor is. It got attention off the bat. It wasn't like Poincaré's findings where it got neglected for 70 years. Almost immediately, everybody was talking about this. Because again, what Lorentz had uncovered, which is the same thing that Poincaré had uncovered, is that determinism is possibly based on an illusion.
Yeah.
That the universe isn't stable, that the universe isn't predictable, and that what we are seeing as stable and predictable are these little periods, windows of stability that are found in strange attractor graphs.
Yeah.
That's what we think the order of the universe is, but that is actually the abnormal aspect of the universe.
Right.
And that instability, unpredictability, as far as we're concerned, is the actual state of affairs in nature.
Yeah.
And I think as far as we're concerned is a really important point too, Chuck, because it doesn't mean that nature is unstable and chaotic. It means that our picture of what we understand as order doesn't jibe with how the universe actually functions.
Yeah.
It's just our understanding of it.
Yeah.
And we're just so anthropocentric that, we see it as chaos and disorder and something to be feared.
Right.
When really it's just complexity that we don't have the capability of predicting.
Yeah.
After a certain degree.
Yeah, I think that makes me feel a little better because when you read stuff like this, you start to feel like, well, the Earth could just throw us all off of its face at any moment. Because it starts spinning so fast that gravity becomes undone. And I know that's not right, by the way.
I've always loved that kind of science that shows we don't know anything. Like Robert Hume, who I understand was a philosopher, but he was a philosopher-scientist.
Sure.
His whole jam was like cause and effect is an illusion. That like it's just an assumption, like that if you drop a pencil, it will always fall down. It's an illusion. And this is pre-gravity, understanding gravity. But he makes a good point.
Pre-gravity when everyone's just floating around.
Yeah. Going, this pencil's got me wacky.
Yeah.
But the point was that, we base a lot of our assumptions or a lot of stuff that we take as law are actually based on assumptions that are made from observations over time. Yeah. And that we're just making predictions that cause and effect is an illusion. I love that guy.
Pretty cool.
And this definitely supports that idea.
For sure.
Sorry, I'm excited about chaos theory. Can you believe it?
Well, I mean, I like that I'm able to understand it in enough of a rudimentary way that I can talk about it at a dinner party.
Well, thank your Bible website. Well, once you take the formulas out, for people like us, we're like, oh, okay, we can understand chaos.
Yeah.
Then when somebody says, good, do a differential equation, you're just like, what?
A what? A different equation?
Right.
All right, so earlier I said that chaos had not been used, the word chaos, to describe all this junk.
Right.
And that didn't happen until later on. And, well, actually, not
70s,
later on.
About 10 years.
But it was kind of at the same time this other stuff was going on with Lorenz.
Yeah.
Late 60s, early 70s. There was a guy named Stephen Smale, Fields Medal recipient, so he's good at math. And he described something that we now know as the Smale horseshoe, and it goes a little something like this.
Boom, boom.
So, all right, take a piece of dough, like bread dough,
okay,
and you smash it out into a big flat rectangle.
Can do.
So you're looking at that thing, and you're like, boy, I hope this makes some good bread.
This is going to be so good.
So then you
put
just...
a little rosemary on it?
Yeah, maybe so. Olive oil, sea salt?
Yeah, and then lick it before you bake it so you know it's yours. No one else can have it.
So you have that flat rectangle of dough. You roll it up into a tube, and then you smash that down kind of flat, and then you bend that down to where it eventually looks like a horseshoe.
Okay.
So now you take that horseshoe, you take another rectangle of dough, and you throw that horseshoe onto that, and then you do the same thing. The Smale horseshoe basically says you cannot predict where the 2 points of that horseshoe will end up.
Yeah.
You can roll it 1,000,000 times, and it'll end up in 1,000,000 different places.
Totally random different places, too.
Totally random. You never know. It's like a box of chocolates. You never know what you're going to get.
You have to say it.
And that became known.
You have to say it.
Oh, what? Imitate Forrest Gump?
Sure.
No, I can't do that.
That's fine.
He's not in my repertoire.
That's fine.
Although I did see that again, part of it recently.
Does it hold up?
Well, I mean, take out 40 minutes of it, and it would have been a better movie.
Eh.
Like all of that coincidence stuff that.
Oh, I love that. I thought that was so charming.
And he also did the Smile T-shirt.
Sure.
Like, it was just too much. Like, he really hammered it too much.
I liked it. That was the basis of the movie.
I know, but see it again, and I guarantee you, like, an hour and a half into it, you'll be like, I get it. Zemeckis.
You know it was a good Tom Hanks movie that was overlooked? Road to Perdition.
Yeah, not bad.
That was a good one.
Great Sam Mendes.
Oh, man, that guy's awesome.
Yeah.
Oh, what is he going to do? He might do something.
He did the James Bond. He did Skyfall.
Yeah, no, he's going to do.
And also that last one that wasn't so great.
He's got a potential project coming up, and he would be amazing for it. And I don't remember what it was.
Did you see Revolutionary Road?
Yes, God. It was just like.
Yeah, you want to jump off a bridge
Yeah.
after you see that movie.
Like every 5 minutes during that movie.
It was hardcore.
It is. He did that one too, huh?
Yeah, and don't see that if you're like engaged to be married or thinking about it.
Yeah, or if you're blue already.
Yeah.
Yeah, just take a really good mood and be like, I'm sick of being in a good mood. Sit down and watch Revolutionary Road.
Yeah. Watch Joe versus the Volcano instead.
Great movie.
Where was I? Smale Horseshoe is what that's called. And he was the first person to actually use the word chaos.
Oh, he was.
I think so. Oh, no.
York was. Tom York's dad.
Yeah, you're right. He wasn't the first person. You're correct.
But Smale's Horseshoe illustrates a really good point, Chuck.
Is it Tom York's dad?
No.
Oh, okay.
No, but they're both British.
Sure. Yorkies.
Actually, one's Australian. No, they're British.
All right.
So those 2 points, which started out right by each other and then end
horseshoe.
up in two totally different places.
Yeah.
That applies not just to bread dough, but also to things like water molecules that are right next to each other at some point, and then a month later, they're in two different oceans.
Yeah.
Even though you would assume that they would go through all the same motions and everything.
Oh, sure.
But they're not. There's so many different variables with things like ocean currents that two water molecules that were once side by side end up in totally random different places.
Yeah.
And that's part of chaos. It's basically chaos personified.
Yeah.
Or chaos molecule-fied.
So we mentioned York. Where I was going with that was there was an Australian named Robert May, and he was a population biologist.
Yeah.
So he was using math to model how animal populations would change over time, giving certain starting conditions. So he started using these equations, these differential equations, and he came up with a formula known as the logistic difference equation that basically enabled him to predict these animal populations pretty well.
Yeah, and it was working pretty well for a while, but he noticed something really, really weird, right?
Yeah.
He had this formula, the logistic difference equation is the name of it.
Sure.
Okay, so he had that formula, and he figured out that if you took R, which in this case was the reproductive rate of a animal population, and you pushed it past 3.
The number 3.
So that meant that the average animal in this population of animals had 3 offspring in its lifetime or in a season, whatever.
Yeah.
If you pushed it past 3, all of a sudden the number of the population would diverge.
Yeah, if you pushed it equal to 3, actually, or more.
Right. It would diverge.
Yeah.
Which is weird because a population of animals can't be 2 different numbers, you know? Like that herd of antelope is not, there's not 30, but there's also 45 of them at the same time.
Yeah.
That's called a superposition, and that has to do with quantum states, not herds of antelopes.
Sure.
That was kind of weird. And then he found if you pushed it a little further, if you made the reproductive rate like 3.057 or something like that, I think it was a different number, but you just tweaked it a little bit, not even to 4. We're talking like millionths of a degree.
Uh-huh.
All of a sudden it would turn into 4. So there'd be 4 different numbers for that was the animal population. And then it would turn into 16. And then all of a sudden, after a certain point, it would turn into chaos.
Yes.
The number would be everything at once, all over the place, just totally random numbers that it oscillated between.
Yeah, but in all that chaos, there would be periods of stability.
Right. You push it a little further, and all of a sudden it would just go to 2 again.
Yeah.
But beyond that, it didn't go back to the original two numbers. It went to another two. So if you looked at it on a graph, it went line divided into 2, divided into 4, 8, 16, chaos, 2, 4, 16, 2, 4, 8, 16, chaos.
Yeah.
All before you even got to the number 4 of the reproductive rate.
Yeah, and he was working with Mr. York because he was a little confounded. So he was a mathematician buddy of his, James York from the University of Maryland. So they worked together on this. And in 1975, they co-authored a paper called Period 3 Implies Chaos. And man, finally somebody said the word.
Yeah.
I kept thinking it was all these other people.
Yeah, and this paper where they first debut the name chaos, they based it, Tom Yorkstead based it on Edward Lorentz's paper.
Yeah.
He was like, you know what? I have a feeling this has something to do with the Lorentz attractor. So that provided chaos to the world, and it was basically the third time a scientist had said, we don't understand the universe like we think we do.
Yeah. And
determinism is based on an illusion.
Like, don't you get it?
Of order
Yeah.
in a really chaotic universe. And this established chaos. It took off like a rocket. In the 80s and the 90s, as you know from Jurassic Park, chaos was everything. Everybody was like, chaos, this is totally awesome. It's the new frontier of science.
Yeah.
And then it just went away. And a lot of people said, well, it was a little overhyped. But I think more than anything, and I think this is kind of the current understanding of chaos, because it didn't actually go away. It became a deeper and deeper field, as you'll see. People mistook what chaos meant. It wasn't the new type of science.
Yeah.
It was a new understanding of the universe. It was saying, like, yes, you can still use Newtonian physics.
Yeah, like, don't throw everything out the window.
No.
You can still try and predict weather and still try and build more accurate instruments.
Right.
And get, decent results. But you can't, with absolute perfection, 100% predict complex systems.
Like determinism, the ultimate goal of determinism is false. It can never be done because we can't have an infinitely precise measurement for every variable or any variable. Therefore, we can't predict these outcomes, right? So you would expect science to be like, what's the point?
Yeah.
What's the point of anything?
No, not science.
Well, some chaos people have said, no, this is great. This is good. We'll take the universe as it is, rather than trying to force it into our pretty little equations and saying, like, if the ocean temperature is this at this time of year and the fish population is this at that time, then this is how many offspring this fish population is going to have.
Yeah.
Say, okay, here is the fish population, here is the ocean temperature, here are all these other variables. Let's feed it into a model and see what happens. Not this is going to happen.
Right.
What happens instead? And this is kind of the understanding of chaos theory now. It's taking raw data, as much data as you can possibly get your hands on, as precise data as you could possibly get your hands on, and just feeding it into a model and seeing what patterns emerge. Rather than making assumptions, it's saying, what's the outcome? What comes out of this model? Yeah,
and that's why, like, when you see things like, 50 years ago, they predicted this animal would be extinct, and it's not. Well, that's because the variations were too complex.
Right.
They tried to predict, and that's why if you look at a 10-day forecast, you, sir, are a fool.
Right. It's true.
Well, 10 days from now, it says it's going to rain in the afternoon. Come on.
But if you took enough variables for weather for like a city and fed it into a model of the weather for that city, you could find a time when it was similar to what it is now.
Yeah. And
you could conceivably make some assumptions based on that. You can say, well, actually, we can predict a little further out than we think. But it's based on this theory, this understanding of chaos, of unpredictability, of not forcing nature into our formulas, but putting data into a model and seeing what comes out of it.
Yeah, and then at the end of that, you learn, like, when that animal is not extinct, like you thought it would be, you go back and look at the original thing, and you have a more accurate picture of how the data could have been off slightly this one value.
Right.
And then you have more buffalo than you think.
Yeah.
Sure.
You got buffaloed by chaos.
And we're not even getting into fractals. That's a whole other thing, and we did a whole other podcast in June 2012 about fractals and the Benoit Mandelbrot.
Yeah.
Mandelbrot.
Yeah.
And go listen to that one and hear me clinging to the edge of a cliff.
Yeah.
Cliff?
Man, we should end this. But first, I want to say there is a really interesting article that's pretty understandable on Quanta magazine about a guy named George Sugihara. Mm-hmm. And he is a chaos theory dude who's got a whole lab and is applying it to real life. So it's a really good picture of chaos theory in action. Go check it out.
Oof.
Okay. If you want to know more about chaos theory, I hope your brain's not broken.
Yeah, go take some LSD.
And look at fractals.
Don't do that.
You can type those words into How Stuff Works in the search bar. Any of those, fractals, LSD, chaos. It'll bring up some good stuff. And since I said good stuff, it's time for listener mail.
I'm going to call this Rare Shout Out. We get requests all the time. And
I'll bet I know which one this is.
Really?
Yeah.
Dude and his girlfriend? Yeah? No?
So far, so good.
Hey, guys, just wanted to say I think you're doing a wonderful job with the show to this date. My first time listening was during my first deployment.
That's the one.
Yeah?
Yeah.
When I listened to your list on famous and influential films, I was hooked after that. Since I came back stateside, I've spent many hours driving to and fro to see my girlfriend, to my barracks, and I can happily say that they've been made all the more enjoyable by listening to you guys.
That's great.
Even my girlfriend Rachel has warmed up to you dudes, which was a pleasant shock to me, as she has told me repeatedly that she cannot listen to audiobooks because, quote, hearing people talk on the radio gives me a headache, end quote. Anyway, I hope you guys continue to make awesome podcasts as I'm headed out on my next deployment. And if you could give a shout out to Rachel, I'm sure it would make her feel a little better that I got the pleasant people on the podcast to reaffirm how much I love her. And that is John. Rachel, hang in there. John, be safe. And thanks for listening.
Yeah, man, thank you. That was a great email. I love that one.
Glad we don't give you a headache, Rachel.
Yeah, for real.
She listens to this though, and she's like, oh.
Oh, yeah. Everybody's going to get a headache from this one. Like, I came to hate the sound of my own voice from this one.
You'll be all right.
If you want to get in touch with us, you can hang out with us on Twitter at SYSK Podcast. Same goes for Instagram. You can hang out with us on Facebook.com/StuffYouShouldKnow. You can send us an email to stuffpodcast@howstuffworks.com. And as always, join us at our home on the web, StuffYouShouldKnow.com.
Stuff You Should Know is a production of iHeartRadio's How Stuff Works. For more podcasts from iHeartRadio, visit the iHeartRadio app, Apple Podcasts, or wherever you listen to your favorite shows.
The next time you end up with something on your shirt, don't turn to your usual detergent. Check out Tide Evo. Tide Evo represents over 10 years of innovation in product development. It's a revolutionary 100% concentrated waterless laundry tile made of compressed microfiber soap layers rather than liquid or powder. It's not pods and it's not sheets. It uses 6 layers of detergent fibers to deliver superior cold water cleaning without plastic packaging. It's mess-free, lightweight, and dissolves quickly. Try new Tide Evo. Real laundry magic.
Hey, quick question for the parents listening right now. When's the last time your kid asked for something and you actually felt good saying yes? Because lately, a lot of families have been hearing the same thing. Can I have Lingo Kids, please?
And here's the thing. Lingo Kids is the #1 entertainment platform for young kids with more than 4,000 interactive games, songs, and shows. Astronauts, wild animals, superheroes, dinosaurs. It's literally everything kids love all in one place.
So when they ask for it, you can actually feel good saying yes. Download Lingo Kids for free and start exploring today, or unlock even more amazing content with Lingo Kids Plus. And if you go with the yearly plan, you can save up to 60%. Just search Lingo Kids in the App Store or Google Play. Lingo Kids, everything kids love.
This is an iHeart podcast. Guaranteed human.